but it is necessary if you want to do something else. And what it's necessary for is if you want to, in this case, if you wanted to rank the patients by the probability that they have Ebola. Right? So it's a slightly different problem. It's not that you have one guy and you're deciding yes or no for him. It's you have one class, the Ebola guys, and you have a bunch of patients, and you want to compare the probability, is this patient more at risk than that patient? That's the question that you're asking. If you want to ask that question, then you need the normalizer, because that probability of a set of symptoms is going to affect things a lot. Now, it's kind of hard to see with the Ebola patient, but we can show an example of that with digits, right? So suppose my goal, suppose I'm trying to separate the digits, and I have a digit 3, and I have a digit 6, and maybe this is my representation of a model for digit 3, right? So I expect all the digit 3s to clump up around this point in space, and this is my representation for digit 6, so I expect them all to clump up around that point, right? And then something happens, and one of my digits, one of my scans gets garbled, or somebody spills ink over the envelope, and I get an observation like that. Now you look at that, and is it a 3 or a 6? It's a 3, right? You as a human have no difficulty figuring out that this is a 3. The problem with this 3 is that to a machine, this 3 looks like nothing that it's ever seen before. Right? So it's never seen examples where there's so much black. So if you try to look at effectively distances between the class models and each instance, this guy is going to be way out there in terms of probabilities, because it really doesn't look like any of the digits that we've seen. So the probability of that observation is going to be very, very, very small. And the reason it can cause problems is you can ask a question, okay, so suppose I am predicting digit 3, right? And I want to rank things by the probability that they reflect digit 3. And if you do that, you'll realize that observation x2, which is clearly a 6, is actually closer to a 3 than that guy. Because that guy is so unlike anything else, it's just way, way, way out there. So 6s look more like class 3 than this guy. And that's kind of a problem. And that's what the normalizer will rectify for you. So the normalizer will compute the overall probability of that observation over all possible classes that you have. Now for this outlier, this p of x given y is going to be a very, very small number. So you're going to add up a bunch of small numbers, you're going to get a small number in the end, and then you're going to divide all the probabilities by that small number. So what it'll do is it'll boost up the posterior probability of 3 to be roughly on the same scale as it is for these guys. So again, it doesn't affect the classification for this outlier, but it makes the probabilities more comparable to other data points, to other instances in your data.